This video is brought to you by Ingenious and their new ECW336, which I recently reviewed and found to be pretty impressive. This is a true Wi-Fi 6E solution. Look at that, it's so awesome. It comes with a ceiling grid installation kit and some other stuff. It's power over Ethernet, but that's a 5 gigabit interface. So they're very, very serious about this. Wi-Fi 6E, 6 gigahertz gives you 14 additional 80 megahertz channels or 7 additional ultra-wide 160 megahertz channels. That means you can do more than a gigabit over Wi-Fi. Yeah, more than wired Ethernet. Yeah, it's possible with Wi-Fi 6E, good range, and the appropriate mesh. I use Ingenious at home. Also use Ingenious cloud products at home. This is the ECW336. If you don't want the cloud, there are non-cloud options from Ingenious, but I really would encourage you to take a look at these because there's no license fees, there's no subscription or anything like that. They'll run, you'll be able to use them, you can set all the features. You get roaming and all that. You don't need any device to manage connectivity, and the configuration, from what I can tell, for the most part is all local. So like once they're set up, if something weird happens to your internet connection, everything will still keep working. And these are very, very impressive pieces of hardware. And so for a small business installation or, you know, the ultra premium home installation, which is what I have, these are pretty solid and I really like them. Thanks to Genius for sponsoring this video, and on with the show. I'm back with the Supermicro 2114GT-DNR. The GT, yeah, it's a very, very nice system. It's a 2U, 2-node system. I did a full teardown with Steve from Gamers Nexus. We've also done some other content here, but I'm here today to talk about the Mi210s that are in this thing. 6 Mi210s, as a matter of fact. That's AMD's Instinct accelerator. What does that mean? Well, I mean, I can do 181 teraflops with the floating point 16, which means that this box is just over a petaflop in less than 2,000 watts of power. This is kind of transformational. The Mi210 is the come as you are accelerator, which is going to work in just about any server grade chassis without anything special. I mean, they're pretty awesome, don't get me wrong, but you know, the Frontier supercomputer at Oak Ridge is the Mi250s, but this node, it's about a half a node, give or take, maybe a little more, depends on how you cut the cheese. But anyway, ROCm 5.3. This is something that I've been working on for the past couple of months. Now, I just got this system, but learning ROCm and the ecosystem and all of that has been sort of an interesting challenge for me personally, because I wanted to look at it and see what all was in there and how it worked and some fun, interesting things. So I'm going to try to do some other interesting content around machine learning and the fun applications that you can have with neural magic and fluid numerics and other folks like that work in and around machine learning and machine learning adjacent systems. For this, though, I thought I could give you a quick rundown of installing ROCm 5.3 on an Ubuntu 22.04 LTS system, because it really is super, super easy. I was able to install it myself in a matter of minutes and get up and running with ROCm 5.3. So much power. Everything is all racked up as before, but this is our 220 volt power cord. It says 20 amps, 250 volts on it, and it really is. This is what we mean when we say top of rack. Nice. Now we just need a little power. So now we will plug this in. Plug that in. Boop. Don't stare into the laser. So we're getting all this hooked up. These are 100 gigabit, color chip media transceivers. And I really don't need these because it's such a short run. But you'll notice that when I plug these in, they don't do anything. I don't get a link light or anything like that. That's because unlike your typical Ethernet switch, these are not pre-configured. They're not plug and play. Well, actually, that's not correct. When you're running this firmware on the switch, it expects to be plugged into the network, and the network will tell the switch what to do. But I haven't done that, so the switch is doing a whole lot of nothing. See, that's how it is in the enterprise. The wire monkey plugs it in, but they're not expected to do anything other than set it up. So we're going to do it the manual way, which involves connecting a console cable, funky RJ45 that's not Ethernet to USB. Serial. I'm super serial right now. Boop. To actually do anything with the serial port, we're going to need Minicom. So now our Supermicro 2-node system is connected at 100 gigabits to our main switch and up to 25 gigabits for all of our other machines, including dual 25 gig for one of our other machines, our 4-node cluster from a while back. So this is going to be pretty cool. Now, it's no secret that NVIDIA and especially their CUDA libraries are kind of the incumbent here. I mean, CUDA as an ecosystem is pretty cool for NVIDIA because it means if you misfire on 1 or 2 GPU generations, it doesn't really matter because your customers are sort of locked into the platform. You have to use CUDA. But AMD is sort of a relentless execution machine. They will chip away and keep working and chipping and working and chipping. And so, initially when ROCm launched, we had, Vega. And Vega sort of evolved into CDNA, and now we're on CDNA 2. We also have RDNA, and there are some folks that want to try to run machine learning accelerators on their individual GPUs, and it's sort of a weird time as far as all that goes. But ROCm 5.3 is a major release. How do we know? Because it makes porting from CUDA a lot easier so that you can move out of that ecosystem. It's an uphill battle that AMD has to climb, but they've been chipping away at it, and now with ROCm 5.3, it's actually shockingly successful at sort of, giving you the tools that you need to not just analyze performance, because it's actually got really good performance analysis stuff too, we'll talk about it in a minute, but also get really good performance from stuff that is available on the internet, Git repositories. It's pretty easy to download and be able to run those applications. It's no secret, the people that are working at Oak Ridge are some of the smartest people, and it's not a coincidence that they chose AMD to build their platform because they wanted an open research thing. I mean, every research scientist I've talked to wants the platform to be as open and consistent and repeatable as possible, and that's kind of what AMD has been building with ROCm this whole time. First, it's the major news that AMD's become a sponsor of the PyTorch Foundation. So if you have something like an Mi210, you will basically at this point more or less have a seamless experience deploying machine learning stuff via Python for your Instinct card. That's huge because a lot of scientists don't really want to fool with things. They just want to be up and running with their code. That's understandable. The second thing is Meta, the company that, has the largest connected graph and probably more data on all of us than anyone, released a bunch of free tools that make it easier to switch your GPU compute platform. That is insanely huge. It sort of suggests that Meta has been evaluating AMD Instinct products continuously for their own internal use, and now they've sort of shared tools with the rest of the industry, which will make it easier to adopt AMD Instinct-based compute devices. There's a kind of a tangent that's also related to that, also related to the Meta release, and it's Intel. So Intel is working on their own GPUs as well. That's no secret. Why does that matter in an AMD video? Well, Intel finds itself in the same position. It's an uphill battle to provide an industry standard so that everybody is not super dependent on CUDA. That makes AMD and Intel unlikely allies. I mean, this is one of the most unusual places where maybe Intel and AMD would be allies, and they're not directly working together on anything as far as I know. Intel's approach for this, of course, is one API, but this is so important to Intel that with the Arc GPU release and some of the other news lately around Intel's GPU division, that even their CEO, Pat Gelsinger, has come out and said, we want developers to be able to write their code once and run it anywhere. Does that sound familiar? Yeah, it should. That's kind of the promise here with everything that AMD is doing on the open side of things. And the AMD documentation is pretty good. Historically, it's had some warts, and it's still got improvement to make. But the ROCm 5.3 documentation for Ubuntu 22.04 LTS installation went really super well, and I was up and running immediately on this insane Supermicro system to be able to run whatever workload. So I've still got a little bit of work to do, and I've got some other fun demonstrations that I want to do while I still have these Mi210s. I gotta send this back pretty quick, so I'm not gonna have a lot of time to educate myself and learn everything that I need to learn in order to put this together, which is why I'm gonna lean on fluid numerics and maybe a little bit on neural engine, maybe with an upcoming launch and some other fun stuff with that, and maybe some other stuff that we can look at to sort of compare. Not every workload runs perfectly in a GPU scenario. I mean, Frontier has one really beefy CPU compute node for every 4 GPU compute nodes, so a lot of stuff runs on the GPU, but depending on what you're doing, that might not necessarily make sense. You got other stuff you have to worry about, but you can still take advantage of the libraries that AMD offers, which is pretty exciting. What exactly is the Mi210? Well, it's a PCIe add-in card, just like a GPU, but it's for compute acceleration. It is 104 compute units with 6,656 stream processors, 416 matrix cores. It can do 22.6 teraflops in floating point 64 vector. Floating point 64 matrix, it can do 45.3 teraflops. Floating point 64 and BF16, that's 181 teraflops, and its peak int4 and int rate is also 181 teraflops. It has 64 gigabytes of HBM2E at a 496-bit bus width. That's clocked at 1.6 gigahertz, so that's 1.6 terabytes per second memory bandwidth. It has full chip ECC support, RAS support, and you can have up to 3 Infinity Fabric links. It is coherency enabled, so you can do dual and quad hives. It supports 64-bit Linux, and is fully ROCm compatible, as I said. It is a full-length card. I did a teardown with Gamers Nexus that I mentioned before. It's a PCIe Gen 4 support. It also supports pass-through SR-IOV, and it's a 300-watt TDP card. It's a 3-year warranty from AMD. Now, with 6 cards in this system with 64 gigs of HBM2E each, yes, that is like 384 gigabytes of VRAM at my disposal in just 2U of rack space and just under 2,000 watts of power. That is an absurd... I can't explain how absurd it is to have a petaflop of floating point 16 in such a small space. I mean, this would be like showing somebody a cell phone from the 1960s. It boggles the mind. Now, one of the most fun things that I saw from fluid numerics is the GPU accelerated Fortran. Fortran, the computer language, if you're not familiar, has a fun and storied history that goes back almost to the beginning of computing. And there is a lot of Fortran software out there in the financial services industry. It's sort of works, and no one wants to touch it. No one has wanted to touch it, and no one continues to want to touch it. So the code continues to run to do things. Fortran makes sense. Because AMD, with their Instinct cards, has come to support OpenMP, Open Multiprocessing. It's a library to make shared memory, multiprocessing compute programming a lot easier. It's so well supported on Instinct that it's pretty easy to get pretty much anything that's designed for OpenMP to work with GPU acceleration. And that includes Fortran. There's actually a whole bunch of languages. You should check out the Wikipedia article on that. But OpenMP is so well supported on this platform that if you have existing code that's designed for OpenMP, getting it up and running on this platform with 6 GPUs across 2 nodes connected by a 100 gigabit Ethernet interface between the nodes, it's actually pretty easy to do. Oh, and if you're into TensorFlow, I was really impressed with how easily Dr. Schoonover from Fluid Numerics was able to port native TensorFlow code directly to what AMD provides in the ROCm setup, so that you can get that up and running, with PyTorch or, well, I mean, whatever that you have. But TensorFlow runs really, really quickly on these cards. AMD includes that in their white paper as well. Just for giggles, to give you an idea of how easy it was to get up and running with these, Ryan did a video on OpenBB, the Open Bloomberg terminal. You can do your own stock trading, and there's a lot of you in the audience that do that. That's pretty exciting. It turns out you can actually tie in these Instinct accelerators with OpenBB, and that works pretty well. Getting ROCm up and running with TensorFlow for AI analysis of data from the Open Bloomberg trade terminal, that's a thing you can do. And having this much compute power at your disposal, if you think you've got a new algorithm that's going to figure out the market and do options trading or whatever crazy thing it is that you want to do, this is a relatively insane amount of horsepower for, if you're a trader, not a lot of money. And it was surprisingly easy to get an AI framework up and running with OpenBB in order to be able to do experiments and things like that. Might actually put that in a different video, although probably would have to bring in somebody that's a little bit more of an expert on the trading side to give us some actually good ideas, because I have no idea what I'm doing on the actual trading side of it. All I can do is janitor the technology together with the best of them. Oh, and in case you didn't know, AMD powers the #1 computer on the top 500, the #1 on the green 500, and the #1 on the HPL AI. That's these cards, the Instinct cards, the very same cards that we're working with here. Remember what I said, AMD and their just relentless execution. Just like in The Shining. Now, because I've got this system configured in a cluster already, if you have something you want to run on here, or you want to try to run on here, hit me up. Let me know what your credentials are and what you're going to try to run, and I'll try to work it out. You can email me, Wendell@level1techs.com, or hit me up on the forum, or whatever you want to do. I just need to be able to download whatever it is and run a script. I can keep it private. I can obscure the data. You can have access to the system. Maybe we can work that out. But let's try some interesting experiments. Does anybody know where NASA put the copy of the space shuttle I can run CFD, computational fluid dynamics, on? I was looking for that the other day and it was sort of MIA. I know the NIST has some really interesting models for CFD, but I need a little bit more of a step-by-step on how to do that. I've got some learning to do. Bottom line, I want to know what the people at Oak Ridge know. I mean, those are really smart people. They picked this system. Why did they pick this system? I want to know why. Why did Meta spend all the time doing what they did in order to better support AMD's ecosystem? And PyTorch, of course, goes without saying. I have a lot to learn. Now, one of the things that was really exciting to me too, and it's a low-level tool, but I want to share, is being able to trace application performance. You see, when you're doing computer janitoring stuff, it's usually a pretty good idea if you have the tools to figure out how things are going wrong. So you sort of learn to figure out how to take a program apart so that you can watch it executing so that you understand better how it works. And that's not always easy to do when you have massively parallel things. Some of the most gifted programmers on planet Earth really struggle with programming in parallel. And no one can program parallel C code, which is why a whole bunch of other languages were invented. At least no human being can, because, unsafe and memory types, and that was a joke. Anyway, the ROCm profiling guide for version 5.3 has a really interesting guide on using their profiling tool to see what your application is doing. What operation is it doing on the GPU? Is it doing compute? Is it doing a memory transfer? Do we have something happening where the GPU spends a lot of time waiting on a memory transfer and then it does a compute? Can we be doing a memory transfer while we're doing a compute? Is that an option? That's one of the example exercises that we saw when we were doing some of the demo code during the fluid numerics training. You can run this tool and actually generate a CSV showing you where your program spends all of its time. And then you can decide to make changes to your program or make optimizations. And this is a skill, in the nicest possible way that I can say this. Some of the people that I fix things for have no idea how to do that or even to really think in those terms, let alone use tools to sort of divine information about the state of things in order to figure out what's going on. So if I had one piece of advice for you, it is to look at these tools that are provided for tracing and performance analysis because they're very good.